Hello, everyone. Welcome to yet another talk about asynchronous programming in .NET. So why another talk? Well, most of the ones I've seen focus on how to use tasks and usually end up with somebody asking in that precise situation that you didn't describe, should I use ConfigureAwait or not? And I believe the reason for that is that those talks focus on how to use this API, but they don't really explain what happens under the hood. So when faced with a new situation, you can't really extrapolate about what you're supposed to do. This time, I'm not going to talk about how to use tasks. Instead, I'll try to break the magic and show you what happens under the hood. And to do that, we're going to re-implement tasks from scratch. Of course, we won't have time to cover anything, far from it. So I'll focus only on the subset of features needed to re-implement async-await. And by the end of the talk, you might still not know whether you need to use ConfigureAwait in that particular situation, but I hope I will have given you the tools to dig into the framework and find the answer by yourself. So let's jump in and start by setting in a bit of vocabulary. If I manage to, yeah, there we go. Task is the Microsoft implementation of the feature and promise pattern, which is a pattern for asynchronous programming. And the way it works is that the user code calls an asynchronous method. And on the side of the method, immediately a pair of objects is created, a promise and a future. And the future is returned to the client. And then an asynchronous operation executes in the background. And when it's done, it signals the promise, which in turn completes the future. And on client side, so after calling the method returns shortly after with the future. Then the client can do other stuff on the side. And when it's ready to fetch the result, it can use the future to get that data. So to give a real-world analogy, it works a bit like if you were pre-ordering some stuff at a store. So you go to the store, you pre-order, they give you a voucher, and then you go back home and live your life. And a few days after there is a product, you can go back to the store and exchange the voucher for the product you pre-order. So that's exactly how it works. And so in the .NET framework, the promise is named task completion source, and the future is named task. And this is the two objects that we will re-implement during this talk. And so for the remainder, I will refer to task completion source as promise and to task as future. So we're going to start with the most basic implementation of the two objects. So here is the most basic feature that we can make. This class has an internal constructor because we don't want user to directly create it. And we have a very simple state. It's either completed or it's not. We don't deal with exception or cancellation. We don't have time for that. And we have simple synchronization. We have one mutex. When we set completed to true, we signal the mutex. And we have a wait method to wait for it. So we can't use by itself. We also need to implement a promise. So I'm going to copy paste it right there. And in the promise, we wrap a future and we expose it in the property. And we have a single method, complete, which transitions the future to completed. So promise is our task completion source and future is our task. And from there, from the user code, you can write this kind of asynchronous method where we immediately create a promise, start an asynchronous operation, and return the future. When the asynchronous operation completes, after 1 second, we just complete the promise. And then on client side, we can call the asynchronous method. Here we do our stuff. And then at some point, we can wait on the future and fetch the result. And so if I run it like this, well, nothing impressive is going to happen. It's just going to wait for 1 second, and then we see it done. More often than not, you will want your asynchronous method to return some data alongside the future. So this is what we're going to implement next. So we need a generic version of the feature that we're going to call feature of t. And we just make it inherit from the feature. And the only thing it adds is a result property, which will contain the result of the method. Then we need a new promise to manipulate it, so a generic promise. So we create a promise of t. And here you might be tempted to make it inherit from promise. But we can't do that, because if we do that, then we get the parameterless complete method, and it means that somebody can complete the promise without setting a result on the future, which will lead to some inconsistent state. So we cannot do that. If you think about it, that's the reason why for so long there hasn't been a non-generic task completion source in the .NET framework. It's because to implement it, since they can't make one inherit from the other, they would have to duplicate the code. And so they don't want to do that unless they have a compelling reason to do so. And a bit of trivia, the non-generic task completion source was merged into .NET Core a few days ago, so it should be finally available in .NET 5. So we can't do that. So instead, we have to copy-paste the code of the promise, and here use a generic feature instead. And of course, the complete method will take a value, and then we just assign the value to the feature. So we will not take care of race condition and this kind of stuff because we won't have time. And so now that we have that, here we can return a feature of int. So we can create a promise of int, and we can complete the promise with the value 42. And then from client side, we can say console.writeLine, feature completed with value. And if everything works properly, then, well, then it should display 42. Hopefully. So there we go. So still nothing very impressive, but you already have the basic tools to do some async programming. But pretty quickly, you will notice one problem is that whenever you need to fetch the value of a feature that is not yet completed, your only way is to call the wait method, which will block the thread synchronously. And so you will be wasting resources just waiting around, which is a shame since one of the points of asynchronous programming is precisely to free those threads when waiting for operations. So to fix that, we need to add a new API. We need to add a notification system that allows us to subscribe to a feature and be called back when it completes. So we are going to implement just that. And I go back to my feature, and I'm going to add that method that we're going to call continue with. I'm going to take an action of feature, which is a continuation. And the idea is that whenever this feature completes, we're going to call this continuation with the feature as a parameter. This way, the continuation can take decision based on the status of his parent. But if we design the API like that, we will be able, of course, to do here feature.continue with. But then if we want to chain another continuation after this one, we cannot because our return type is void. So it would be much more convenient to instead return a feature. And the convention will be that this feature completes when this callback is complete. And this way we can create a workflow. So to implement this, we can use our promise object, but for optimization purpose, to reduce the number of allocation, it's better to have one type dedicated to this. And so we're going to introduce a new type of feature that we're going to call feature continuation. I'm going to copy it here. So it's very simple. It inherits from feature. It takes the continuation and the parent feature and store them. And then it explores an invoke method that is internal, that's very important, that calls the continuation and transitions the feature to completed. So basically, it merged the concept of feature and promise into a single class, mainly to reduce the number of heap allocation and also to make some stuff easier to implement later. So once we have that, we can go back to our continue with method and implement it. So it will be something like that. We create our feature continuation. We call an add continuation method that we haven't implemented yet. and we return the future. But if I have only this continue with, then here, let's say that I want to return the value, so say 10. I won't be able to because our only continue with return a non-generic feature, and we have no overload that returns a generic one. So we're going to add this. So like this, I declare this overload. So continue with that take a func instead of an action this time, and it returns a generic feature. And so I'm going to copy paste the code here, but it's not going to work because feature continuation is a non-generic feature. And here we need to return a generic one. So we need a new implementation of feature continuation. So we are going to do that. And here we have feature continuation of t, which is just like feature continuation, except that it inherits from future of t. And so it takes the continuation and the parent. And in the internal invoke, it calls the continuation, assigns the result to the future, and transition to completed. And so now I can just use my generic feature continuation, and this should work. But then let's imagine that I don't want to return 42, but I want to return the value of the parent feature times 2. I can do that because continue with is only declared on the non-generic feature. So I need to add overloads on the generic one. So we're going to do that right now. So my generic feature is right there. And so I need a continue with on this class. And here you may be tempted to copy paste this, but this is not going to compile because feature continuation accepts an action of feature. And here we have an action of feature of t. And so if you want to do things cleanly, you have to implement not 2 types of continuation, but 4 different types of continuation. And that's what I did in the .NET framework. So in our case, we're going to cut corners just to go faster. And I'm going to reuse the same feature continuation, but introduce a lambda that will cast the future to future of t. But by doing so, I add a heap allocation because of the closure. And so if you're worried about performance, you cannot do that. And that's why they didn't do that in the .NET framework. OK, so I still need the one for that return a generic feature. And now we can finish implementing it. So we still don't have the add continuation method, so I'm going to implement it. And we just need to enqueue the continuation to some internal queue. And I have a to-do here. I will go back to it later. And so I still need to introduce that concurrent queue. So concurrent queue feature that I call continuations. There we go. And so right there, this works. And we have our continuations that are enqueued, and we still need to execute them when our feature is completed. So I'm going to introduce an invoke continuations method. I'm going to copy paste it right there. And the idea is that we just take everything we have in the queue and we call invoke on it. But this cannot work because invoke is an internal method that is declared on future continuation and future continuation of t. And here we have a queue of future, so we cannot use invoke. So there are multiple ways to fix that. For instance, we could do some casting, but we have potentially 4 different types of continuation. We could use interfaces. But the way they did that in the .NET framework is by introducing an internal virtual invoke method on the base feature, and then just overriding it when necessary. Right there, and my other feature continuation is right there. So it means that if you call invoke on some kind of feature, you will get an exception, but this should never happen because the method is internal, and on our side, we're careful to only call it when it makes sense. We still need to call invoke continuation some point. So we're going to say, when I set is completed to true, I'm going to call invoke continuations like that. And yes, and the to-do. So if I add continuation of feature that is not completed, is going to be enqueued. And then when we transition to completed, we call invoke continuation and we execute it. But if the feature is already completed when I call add continuation, then I'm going to enqueue it and never execute it because we've already called invoke continuation. So in that case, I'm going to say, okay, if the current feature is already completed, so I directly invoke the continuation without enqueuing it. And with that, we should have everything we need. So I'm just going to put that in there. And I'm going to chain another feature after that, so continue with. Here, I'm going to say second feature completed and display the result. And we're going to make sure that it's working. And we see that done is displayed right away because we are not blocking the thread anymore. And then we see 42 and 84. But we still have a problem. Let's say that I want to add a continuation to the first feature. So I'm adding a continuation to the feature that was returned by async method. And here I'm going to write a second continuation, like this. And then I'm going to make the asynchronous method slightly faster, just to save time. And we will say that the first continuation takes some time to run. And now if I run my program, what is going to happen is that we have done instantaneously, and then we have a 2-second pause, and then we have a feature completed that is executed first, then second feature, and finally second continuation. So second continuation had to wait for those two to execute before executing, even though it should have been able to run as soon as the asynchronous method completed. So what happened? The problem with our current implementation is that we are calling the continuations in the same thread that completed the promise. This is something in asynchronous programming that we call inlining. And this is a very fine optimization in some cases, but there are other cases like that where this is not a desirable behavior. So to work around that, we need to introduce a way to schedule our continuation on another thread. But depending on the application, they may have different requirements for scheduling. So we're going to introduce an API for that. So I go back to my implementation, and I'm going to introduce this API that we are going to call Future Scheduler. And the idea is that we will introduce a single method that is queueFuture. And whenever you implement your own scheduler, you override this method, and you get called back whenever there is a feature to schedule. And then it's up to you to pick when and on what thread this feature should execute. So we are going to implement a scheduler ourselves. So this is a thread pool feature scheduler. So we're going to schedule the feature on the thread pool. We override queueFuture. And here we're just going to schedule it on the thread pool. And you may be thinking, that's it, it's going to work, but let's imagine that I'm inside of my feature library, so I have access to all the internals. But if I'm in my application, so in a different assembly, and I try to do the same thing, then I'm going to have a compilation error here because invoke is internal. And we don't want to make invoke public because there are situations where we shouldn't call invoke. So we want to prevent that. So ideally, we would need a way for the user to execute the feature that was given to him through the queueFuture method, but only this one. And the way they fix that in the .NET framework is by introducing a protected method that we're going to call executeFuture, which takes a feature. And here we're going to make some sanity check to make sure that this feature is the same as this one. And then we call invoke safely. Sorry, it should be on the base scheduler. There we go. And so when we implement our own scheduler, instead of invoke, we should do executeFuture. And this should work as expected. So we still need to wire everything up. Whenever we do continue with, we enqueue the feature. But now we will now accept feature scheduler. And the idea is that we enqueue the feature, but we should also enqueue the scheduler. And one way to do that is to add the notion of scheduler to our feature continuation. And in fact, it's even easier for many reasons to add the notion of future directly to the parent future. That's what they did in the .NET framework. The notion of scheduler is backed directly into the task. So I'm going to add to our internal constructor the scheduler. I'm going to store it in a property. And then I'm just going to update all of our constructors to make sure we take the scheduler. So I do that for future of t. And I'm going to do that for future continuation as well. So here I just take the scheduler, and then I call the base scheduler. And if the scheduler is null, then I will give future scheduler.default. So I'm going to add that in a second. There we go. And then we are going to define the notion of a default scheduler just to make things easier. So static read-only future scheduler default, and we return the thread pool scheduler. And now we should have pretty much everything we need. So we just need to replace the parameter in all of our continue with call. So basically, I take the scheduler and I give it to the future continuation. And I do that everywhere. So we're just going to skip around it. There we go. But I'm still not using the scheduler. So to use it, I'm going to add a helper that I'm going to call schedule and start. And what it does is asking the scheduler to enqueue the future. And now every time I was using invoke, I will be using schedule and start instead. And so if I forgot nothing and I run my program, we see that second continuation appears immediately without waiting for the other continuation to execute. So we've solved the scheduling problem. But we went from a situation where everything was inlined to a situation where nothing is inlined. It would be nice to have a situation in between where we inline only when it's safe. So we are going to add the notion of inlining to our scheduler. So we will add a protected internal virtual bool try execute future inline that takes a future. Default implementation returns always false. And then in the thread pool scheduler, we're going to say, okay, it's fine to inline if we are currently on the thread pool. So if the current thread is a thread pool thread, then we execute the future. And we return true to say, okay, we've inlined the future. Otherwise, we return false. So the idea is that you implement this, you get code whenever there is a possibility to inline a future, and then you take the decision to execute it or not, and it returns true if you did, or false otherwise. And then we still need to decide when it's safe to call the inlining. And we will say that it's safe whenever we have only one continuation in our on our future. So right there, I'm going to say, okay, if we have only one continuation, then I take it, I give it to the scheduler, and I ask, do you want to inline this future? And if the scheduler refuses, then I just schedule the future as usual. And of course, you can think of many situations where it's safe to inline a future or not. And in fact, you have different rules between .NET Framework, .NET Core, and Mono. Here we will only implement this one. Just to make sure that it's working, I'm going to add a diagnostic message right there, so inlining. And if I run my program, we see second continuation, future completed, and only there I see inlining because this is the only place in my workflow where I have only one continuation. Also, I forgot one to do, sorry about that. Right there, in execute future, we still need the sanity check to make sure that this feature is the same as this one. Well, now that we have the notion of scheduler inside of our future, we can just say, okay, if the scheduler of the future is different from this, then it means that the user is trying to do something funky, and we throw an exception. Okay, so at this point, we have everything we need from the task. So just to summarize, The types that we have re-implemented are future for task, promise for task completion source, future continuation for continuation task from task. And as I explained, there are 4 different types of continuation in the .NET framework. And future scheduler for task scheduler. And so now, if you need to implement your own scheduler for your .NET framework application, you should be able to understand what you are expected to do inside of queue task and try execute task inline, because they work the same way as what I described. Okay, so we can't talk about asynchronous programming in .NET without mentioning async-await. So I've got an API here with a few asynchronous methods. Some of them are private. And the idea that we wait for an asynchronous delay, and then we return a hard-coded value. So 1, 10, 100, and do something else, takes an input and double it. And so in modern C#, you would be able to write this. Basically, you would be able to mark your method as async, and then use the await keyword to change your call, just like if you were writing synchronous code. And then something magic happens at the compilation and it works. And we're going to re-implement that magic. So whenever you mark a method as async, the compiler is going to emit what we call a state machine. So it's going to be a class that is nested inside of your parent class. Why is it nested? Because it needs to access to the same method that your asynchronous method, even if they are private. And then it will declare a few fields. First, a state, because it's a state machine. Then a reference to the instance of the parent class if the method is not static. Then a move next method, which will contain the core of the logic. And then it needs to declare a promise. So a public promise of int. Here we return a future of int, so we declare a promise of int. And there we go. And then the compiler is going to rewrite your call async method into this. Call async, sorry. So first it creates the state machine. Then it assigns the this field. Then it could move next. And whenever move next returns, it returns the future that is associated to the promise. So it doesn't look like your original method at all. And now from our code, we are not going to need this anymore. We can call a new API.callAsync. We can wait for it to complete. And then we can just display the result. So if I run this right now, nothing is going to happen because my state machine is empty. And now we're going to implement it. So the state machine is basically a giant switch case. So we switch on the state. And the first time, the state is 0. So we update the state so that the next time we call move next, we will move to the next branch of the switch. Then we need to call do something async 1 and await it. So we are going to say, okay, this do something async 1, which returns a future, and we're going to add a field to store it. Like this. And then we need to wait for this feature to be completed. So we are going to call continue with and ask, okay, when this feature completes, just call me back, call back the move next method. And since we've updated the state, when the feature completes, it will call move next, and we will move to the next branch of the switch statement. And here we can't do anything else, so we're just going to return. That's important. It means that we will freeze the thread. So here we will return, and at this point, we will return the feature to the client. So whenever you call an asynchronous method, it's going to execute synchronously until you get the first time you await an asynchronous operation, and then it's going to return to you. Okay, so the next time it's going to be case 1. So we update the state just like before. And so the feature completed, and we need to assign this feature to the I variable. So we are going to add a few fields to our state machine to keep track of the local variable. And I'm missing one, of course. There we go. And I'm going to fetch the result of my future and store it into I, like this. And so now we've implemented the first line, and we need to do the same thing for every line of our asynchronous method. So here I'm just going to copy paste stuff. So after that, we could do something async2, we call continue with, and we return. Next case, we fetch the result into J, we could do something async3. Next case, we fetch into K. Now we could do something else async, and we give all the local variables that we stored on our state machine. And the last case is a bit different because it is the last one. And here we're going to complete the promise, which will in turn transition the future to complete it. And so now if I run my program, we wait for a while, and here we see the value. So our method executed properly. So there is a nice optimization that we can do here. The problem is that do something async will sometimes execute synchronously. And when that happens, we're still going to call continue with, which may schedule us to another thread, only to be called back. So it would be nice if when this executes synchronously, we just directly jump to the next state of our state machine. So we're going to do just that. So I'm going to say, okay, if future is completed, then go to case 1. And then we do that for every branch. So should understand that because of that, if all of our await call, complete synchronously, then our async method will complete synchronously and will not return before the end, because every time we jump to the next case and we don't call return. Okay, just making sure that I block nothing. Okay, so here we have a working state machine, and the one in the .NET framework uses the same principle. Of course, it's much more complex because it has to deal with try-catch block, with if-else, with while loop, and so on. So there are many more states, and it can jump back to a previous state and so on. But the basic principle is the same. But for right now, I can only await a future because my state machine only knows how to manipulate a future. It would be nice if we could just await any arbitrary type, such as task or value task, or even your own custom future. And to do that, we're going to introduce an abstraction. We're going to call this abstraction IAwaiter, which will define what we need to await something. And here we're going to say, okay, what do I need from the future? I need to know if it's completed. I need to change the continuation, and I need to fetch the result. So I'm going to add those 3 things to my abstraction. So get result is completed and uncompleted to change the continuation. Then I'm going to introduce FutureAwaiter, which is the implementation of IAwaiter for our future. So all it does is take a future, store it, and then we just map every method of the API, of the interface, on our future. So uncompleted is mapped on continue with. And once we've done that, we can say that the convention is that whenever you await something, we will call getAwaiter on that something, and we expect to get an IAwaiter, and then we know how to use it. So here I will replace this by a FutureAwaiter. And here, whenever I await something, I use getAwaiter. Oh yeah, and I also should add the getAwaiter method. Sorry, I'm skipping one step here. So I add a getAwaiter method to my future. I write it as an extension method, but it could be a normal method. It will work the same. And when you call getAwaiter, we return a new FutureAwaiter for that future. So now I can use getAwaiter. And here I'm just going to replace everything by the API of getAwaiter. So uncompleted. And results become getResult. So I'm just going to replace everything. I'm just going to copy paste to go faster. So like this. So it's the same state machine, except that I replace the call with the IOWaiter API. So making sure that I broke nothing, and it's still working. And so at this point, we can await any type that define a getAwaiter method that returns an IOWaiter. So that's pretty nice. But we can await anything, but we still have to return a future because we only know how to manipulate this promise. So just like the awaiter, it would be nice if we abstracted that so that we can return any arbitrary kind of future, so that we can return a task, a value task, you name it. Just like before, we're going to introduce a new abstraction, and we're going to call that an async method builder, and we will call ours the future builder. And then we see what do we need from the promise. We need to fetch the associated future, and we need to complete it. We need only those two things. So I'm going to add those two things to my future builder. So we create a promise. We have a task property which returns the future, and we have set result which completes the promise. Okay, and I'm going to add one more thing. Right now, it's my state machine that calls uncompleted on the awaiter. I want to delegate that to the builder so that it will give the builder a chance, for instance, to log some stuff or to save the state before yielding the thread. It's just to make the API more powerful. So I will call this method await uncompleted, and it will take an awaiter and a state machine. And then the most basic implementation, we will just call the awaiter and ask to call back the state machine. But right there, we could save the state or log stuff or whatever. So this is not going to compile. I cannot reference the state machine because every asynchronous method will have a different state machine because it's emitted at compilation time. So for that, we're going to introduce an interface that we will call async state machine. And it has a moveNext method. And so here I can expect an async state machine, and this should compile. And here I'm just going to say that I implement async state machine, that I have a future builder instead of my promise. I will call it builder. And I just need to replace everything. So here we return builder.task. And instead of future.uncompleted, we will builder.await uncompleted, like this. And in the end, we will call builder.complete, .set result. So just like before, I'm going to copy paste. There we go. So here we call builder.set result. And now just making sure it's still working. And this is still working. So right now, our state machine can await any arbitrary type and return any arbitrary type. So it's pretty nice. From this point, we're going to optimize some stuff. And mainly, I would like to reduce the number of heap allocation because when you allocate something on the heap, you put pressure on the Gosse, and it can cause unwanted pauses in the client applications. So we will start by our builder, and we will make it a struct to remove one allocation. You can't have initializers in a struct, but in any case, I don't want to manipulate promise because it will add one heap allocation that we can remove. So instead, we will directly manipulate a future. And in the task property, we will lazily allocate that future. So if it's not there, I create it, and then I return. And so in set result, I'm going, since I don't have a promise, I'm going to manipulate directly the future. It's okay because it's in our library. And I use the task property so that it gets allocated lazily if it's not already allocated. And one more optimization. Here, when I call await uncompleted, I expect an IOWaiter. And my future awaiter is a struct, which means that it's going to be boxed. Why? Because structs are value types and interfaces are reference type. They are different semantics. And so for you to be able to cast your struct to an interface, the runtime is automatically going to box it, which means it's going to make a copy of it on the heap. We can avoid that by making our method generic. So instead of expecting an I-awaiter, we expect a T-awaiter where T-awaiter is an I-awaiter, which looks dumb like that. But by doing so, you remove the heap allocation, you remove the boxing. So just making sure that it's still working. Still good. So we're going to optimize further. Now, let's have a look at our state machine. Right now, it's a class. It would be nice if it was a struct. So fun fact, in the .NET framework, if you compile in debug mode, the state machine is a class. And if you compile in release, it's a struct. That's because it's much easier for the debugger to keep track of it if it's a reference type. And so in debug mode, it's sacrificing the optimization just to make debugging easier. So I cannot have an initializer, but I don't care because future builder is a struct, so I don't need to new it. And that's it. Looks like it compiles. But if I run my code, here I'm going to wait forever because it's not actually working. And so we're just going to add a few breakpoints to see what's happening. So one here and one in when we complete the builder. There. If I run my program in debug mode, so here we see that call async returned, and we are waiting on the future. So far, so good. Then at the other end of the asynchronous workflow, we're going to call set result on the builder, which will transition the future to completed. But here, if we inspect underscore future, we can see that the value is null. So it's going to be lazily allocated when we call the task property. But that's really weird because we are already waiting on the future at the other side. So how can it be null? Well, this one is a bit hard to understand, so I prepared an animation for it. And so there we are. So we have a very accurate representation of the memory with the stack on the left and the heap on the right. And this is our code, a bit blurry. And so we create the state machine. The state machine is a struct, so it gets allocated on the stack. The future builder is a struct as well, so it gets nested inside of the state machine. That's how structs work in .NET. Then later on, we call await and completed. And here we're going to box our state machine. We're going to do so at two places. First here, because we cast it to an interface. So that's what I explained for I-awaiter. This is going to cause boxing. And here, which is less obvious. Why? We box here because we take a delegate to an instance method of a struct. The problem is that the struct lives on the stack, and the stack will get cleared when the method returns. But the delegate can live pretty much forever and can be called at any point in time during the lifetime of the application. So by the time my delegate is going to be called, my struct might not be on the stack anymore, which will cause us to reference invalid memory. So to make this safer, whenever you take a delegate to an instance method of a struct, the runtime automatically boxes it. So why is that a problem? Well, when you box something, as I explained, the runtime is going to allocate a chunk of memory on the heap, then it's going to make a copy of the stack to the heap. And so at this point, we end up with two different state machines in memory. Then later on, we're going to call wait, which will cause a lazy allocation of a future. And this is going to be allocated on the future builder that is on the stack. So the one on the left now has a future that has been lazily allocated. And then at the other end of the workflow, we're going to call move next on the boxed state machine. And later, we're going to call set result again on the box state machine, which will cause the lazy allocation of a future on the box state machine. But then we end up with two different futures. And so if we complete the one on the right, the one on the left still isn't completed. So how can we fix that? Well, the most obvious fix is to get rid of the boxing. And we can easily get rid of the first box because we did that for I-awaiter. We can just make our method generic. The second one, we can't get rid of it. It's a runtime limitation, so we have to live with it. Instead, right there, we're going to force the allocation of the future. So what does it change? Well, the idea is that we force the allocation of the future while our state machine is still on the stack. So now we have a future in our future builder. And then when we get to the next line and we box the state machine, we make a copy of it. And so we make a copy of it with the future inside of it. And so now if I call set result on the right, it completes the one on the left because future is a reference type, and so both of them reference the same object. Please note that it can only work because future is a reference type. And that's why in .NET Framework, when you use value task, which is a struct implementation of the task, if you await an asynchronous operation, it will have to do a heap allocation under the hood, precisely because of that problem. All right, so we're going to implement the fix that I mentioned. So I just need to go back to my builder that is right there. I'm going to make it generic to prevent the boxing. Note that I also add the ref keyword. I didn't explain that. That's because now that I expect a struct, whenever you call a method and give a struct as a parameter, you make a copy of it. And since we make a copy of it, we end up in exactly the same problem as we had with boxing. So by using the ref keyword, I make sure that we don't make a copy of it. So here I need to force the allocation of the feature, sorry. So I need to call the task property. I cannot call an empty property like that. That's not valid C#. So I like to use the GC keep alive method, which is an empty method, just to make it valid. But I could do that, and that would be the exact same thing. It's just a matter of style. And so if I run my program right now, and if I made no mistake, hopefully, oh yeah, since I added the ref keyword, I need to update all the call sites to give the ref parameter. So there are 4 of them, sorry. There we go. So now if I run my program and if I make no mistake, now this works and our state machine is a struct. That's one last optimization I would like to do. Right now, every time we call await uncompleted, we box the state machine right there. But every time it's going to be the same state machine. So it would be nice if we boxed it only once and then we stored the box state machine somewhere. So we're going to implement that. I'm going to add a field to store the state machine like that. And then here I'm going to say, okay, if state machine is null, then I box it. So to box it, I just cast it to an interface with an equal is better. And then I store it in my underscore state machine field. And of course, I call move next on the box state machine. So I thought that was working, and then I added a diagnostic message. So right there, I'm going to write boxing. And if I run this, we see that boxing is displayed every time we await. So our optimization is not working, which is really weird because it's very straightforward. If state machine is null, we assign it, and so it shouldn't be null anymore. So this one took me actually an entire afternoon to understand. So I have an animation for it. So we have the same representation as before with the stack and the heap, and this is our code. So at this point, we have the state machine on the stack, and we get to this line where we're going to box the state machine. And since we box it, I've already explained, we make a copy of it on the heap. And then we are going to assign our underscore state machine with a pointer to the box state machine. But the problem is that we assign underscore state machine to the this parameter. So we assign it to the state machine that is on the stack. Okay? And then later we call awaiter on completed and we return. So the stack gets cleared. Move next get called at some point on the state machine on the heap. And then during the execution is going to be unboxed. And we end up with a copy of the heap on the stack. And then nothing references the state machine, the box state machine anymore, and it's going to get garbage collected. And we get back to the initial situation. We are going to box the state machine. We're going to assign it to underscore state machine, but we assign it to the one on the stack. And the problem is that we never assign it to the one on the heap. So it's pretty much the same problem as we had with the feature just previously. And so you may think we can fix that by boxing the state machine only after assigning the underscore state machine field. But we can't do that because to assign the field, we need to box the state machine first. So it's a kind of chicken and egg problem. To fix it, we are going to use this bit of code. So let's see. First, we box the state machine, just like before. Then we assign it to underscore state machine, just like before. And then we call set state machine on the box state machine, and we give the box state machine as parameter. So that looks weird. So first, it's very important to understand that we call set state machine on the box state machine. So I call it on this one, not the one on the stack. Then inside of set state machine, we're going to call builder.setStateMachine. Since we are in the boxed state machine, we will call set state machine on the boxed future builder. And then we just assign the underscore state machine field. And so we end up with the underscore state machine field that is assigned inside of our box. And our optimizations will work from there. So we're just going to implement it real quick. So the idea is that right there, I copy paste the same code as the slide. And so it means that we're going to need a set state machine method on my builder. So right there. And a set state machine on my async state machine here on my interface. I'm going to copy paste this like that. And now we need to implement it on the actual state machine. So right there. And now if I forgot nothing, if I run my code, we see that boxing is displayed only once and is still working. At this point, we've implemented all the features that are needed to make async-await work in the .NET framework. And to prove it, I'm going to go back to our future of T implementation, that is right there. And I'm going to add the async method builder attribute. It tells the compiler, whenever I make an asynchronous method that returns a feature, use this builder, okay? Then I'm going to add the iNotify completion interface to the IOwaiter. This is just the IOwaiter of the .NET framework. And then I'm going to delete the async state machine because it already exists in the .NET framework. So here now we reference the one that is in the .NET framework. And I'm going to add a few things to the builder because I took some shortcuts. So first I need to add a create method which creates a new builder. That's all it does. And we are going to add a start method which call move next on the state machine. So why? Because I lied to you. Here, when you use the .NET compiler, what it does, it doesn't call move next on the state machine. It calls start on the builder, which in turn call move next on the state machine. This is to give the builder a chance to do some initialization or change the state or change the thread and so on. But right now, we just call move next on the state machine. Then I'm going to add a set exception method that we're not going to implement because we don't have exceptions in our future. And last but not least, we are going to add an await and save uncompleted that I don't have time to explain, but it has something to do with the execution context. But here I just call the traditional await uncompleted. And now that I've done that, I can delete this, I can delete this, and I can just uncomment this method, and it should compile and work just fine. And so we see our boxing once, and we have the expected result. And so we've re-implemented basically async await in the .NET framework. All right, one last thing. We cannot talk about async await without mentioning the synchronization context. And so what is a synchronization context? So if you are used to making WinForm or WPF application, you may already know that you can only update UI controls from the UI thread. The synchronization context is an abstraction that allows you to send your calls back to the UI thread to make your life easier, basically. And so here I have a synchronization context, not going to show it. And instead of calling call async like this, I'm going to call it on the synchronization context. So basically, I use the post method of the synchronization context, and it says, OK, execute that call on the UI thread. And then in call async, I'm going to instrument it with the display current synchronization context method, which name is self-explanatory. And I'm going to run the code. And here we see that the first time we are on our custom synchronization context, so we are in the UI thread, and then we await, and then we are outside of it. That's because our future scheduler put us back on the thread pool every time. And so if you are writing a UI, it means that right there, you can update your UI controls, and there you cannot anymore, even though you are in the same method. So this is very error prone. And so to fix that, we would like to stay in the UI thread for the duration of the method. So we're going to add this feature to the feature awaiter. So in the feature awaiter, whenever it's completed, we use continue with to call back. So instead, what we're going to do is first, we capture the synchronization context. And then in the continue with, we're going to post the continuation back to the synchronization context if there was one. Or if there's none, we just resume the execution normally. And now if I run my code, we see that we stay on the synchronization context for the entire while of the method. But so if you're a UI guy, then you're happy. But if you are writing a library, then you're not so happy because your library is going to be hosted in many different applications, and all of them might have a different synchronization context, even custom one. And so you don't want to resume execution in their synchronization context because it may have subtle rules for threading, which could cause deadlocks in your code. So basically, we should add a way to opt out from this behavior. So, okay, we are going to update the awaiter again. So I go back to the feature awaiter. I'm going to add one parameter. We're going to call it capture context. And then we're going to say, okay, we capture the synchronization context only if capture context is true. Otherwise, we don't capture it. But then we have a problem. When we write our asynchronous method, we just say we await that, and then the compiler is going to call getAwaiter on whatever this method returns, but we cannot give a parameter. And so we cannot feed the value of capture context we want to our feature awaiter. So the way they fix this, and so here in the parameter let's getAwaiter, we must choose true or false, but we cannot have both. So the way they fix that in the .NET framework is by introducing another type that we're going to call configured feature awaitable. And all it is a struct that contains a feature and a value for capture context. And it exposes a parameter let's getAwaiter, which returns a feature awaiter with the value we want. So how does that help us? Well, now that we have that, we can add an extension method. So they are here, that we're going to call ConfigureAwait. And ConfigureAwait will take the Boolean and create the configure feature awaitable with the value we want. And then the state machine will call getAwaiter on that type and get the feature awaiter that is properly configured. So this is just a workaround for the fact that whenever you await a type, you cannot give a parameter to your awaiter. So now let's say that as a second call, I do ConfigureAwait false. Oh, sorry. So remember that ConfigureAwait does not do anything to the task. All it does is create an intermediary type that will return a properly configured awaiter. That's all it does. And so if I run my program, here we can see that for the first few calls, we are on the synchronization context, so on the UI thread. And then we await with ConfigureAwait false, and then we are back to the thread pool. And that's exactly how ConfigureAwait works in the .NET framework. And so you see that if you do not use await, and more precisely, if you do not use the uncompleted method of your awaiter, then ConfigureAwait will have no effect at all on your program. All right, so that's it. That's a lot of content for just 1 hour. I hope you appreciated it, and maybe we have a bit of time for questions, and otherwise I will be hanging around on Slack to answer them.